Hello, I'm really honored to have this opportunity to present a message that has emerged for me over the past decade about data science, one of the 21st century's most important innovations. Namely, that data science is far more than a current trend. It introduces entirely new paradigms of discovery and of computation that we are just beginning to understand. I hope to convince you of its significant potential and risks and what needs to be done to ensure safe, robust data science, and then introduce my research to that end. So please consider with me data science in the big picture and speculate with me as to its significance and future in 6, hopefully provocative hypotheses, such as this one, on its impact. We'll return to this hypothesis at the end of the talk. Every few centuries, a new paradigm of discovery arises. Data science is the fourth. So 3 times in history, a new paradigm of discovery has arisen to become one of the greatest achievements of its age. They matured over centuries and transformed our understanding of the world with new reasoning and problem-solving paradigms, like the scientific method that we all learned from childhood. Data science, on the other hand, is in its infancy with a new inscrutable paradigms. Why inscrutable? Let's look at 7 fundamental differences between data science and the scientific method. The scientific method can analyze phenomena under strict controls. Data science can analyze any phenomenon for which there is adequate data, thus explaining the amazing breadth of applicability of data science. Second, scientific results are deterministic. Your hypothesis is either true or false. Data science, on the other hand, results are probabilistic. They may be true. Third, the scientific method tells you why something happened. Data science typically discovers what may have happened, but not why. Fourth, the scientific method analyzes empirical data obtained under empirical control. Data science analyzes observational data that merely needs to include the features of the phenomenon being analyzed, with no control on collection. Fifth, the scientific method is hypothesis-driven. You create a hypothesis and design an experiment to prove or disprove it. Data science can be hypothesis-driven, but more importantly, it can be data-driven. It can look to data to learn patterns. Sixth, empiricism is limited to relatively small models, typically less than 5 to 10 variables. Data science can analyze models with hundreds of billions of parameters, models beyond human comprehension. Seventh, complex scientific experiments can take months or years. Data science, on the other hand, accelerates discovery in many ways. First, it can look at billion variable models in hours or days. Secondly, it can be used to reduce a vast search space to a few probable results that could then be resolved by conventional means like empiricism. So each difference makes sense, but none of them really explain the new reasoning or problem-solving paradigm, as we will see later. Data science also introduces a new computational paradigm. In conventional computing, humans write, analyze, and improve code that is repeatable, producing the same results given the same input. In data science, a neural network writes and modifies itself, but is not repeatable as new data modifies the model. We don't understand how it works or why a result was produced. However, we must understand it to ensure safe, robust data science. So let me clarify a few concepts for this talk. I'll refer to data science, machine learning, neural nets, and in one case, AI, interchangeably, but recognize that they are different. Data science is often defined as the extraction of valuable insights from data. One of the takeaways from this talk is that data that is not precise. Data science is the principled extraction of valuable insights from models. Models that are mathematical models with a data component, often called the data model, and an analytical component, often called the analytical model. And the fact that an analytical model always has a corresponding data model is often ignored in data science. My approach to safe and robust data science is based on mathematical models that can be defined by principles such as robustness. Another fundamental concept in data science is the workflow, the backbone of data science. Data science is conducted in 8 tasks, each relying on concepts from different disciplines. For example, data task concepts typically come from data systems, while analytical task concepts come from machine learning. Yet they both produce a model, a mathematical model, which they exchange. Recognizing this, researchers have unified the 2 tasks, achieving a 2,000 times performance improvement over TensorFlow with increased accuracy. This illustrates that data science is model-driven and that cross-disciplinary collaboration can be extremely rewarding, and it is just beginning. Finding the same concept applied in different disciplines, in this case, the mathematical model, leads to a far better understanding of data science. This example also demonstrates that data science is in its infancy because there will be many more substantial developments like that one. So, returning to our original hypothesis, will data science with its new paradigms transform our world? That is, how significant will data science become? To see what it means to transform our world, consider past transformations. For 150,000 years, at the beginning of human history, change was local and the rate of change was linear. 250 years ago, change was driven by technology, the Industrial Revolution, steam, and electricity, but change was still predominantly local with factories and electricity in the developed world and linear in the number and speed of innovations. According to Yuval Harari, in the last 100 years, man created the means to eradicate the 3 greatest threats to mankind: war, hunger, and disease. Yet change continued to be mostly local with some global impacts and linear in the number and speed of innovations. It's only over the past 50 years that technology-driven innovation has led to both global and exponential change in both number and speed of innovations. For data science to transform our world, it would have to be at this scale, addressing existential threats like saving the planet or saving humanity. This may seem pretty far-fetched, but James Watt had no idea that his steam engine would transform the world. Let's see what experts say about the potential significance of data science. Alphabet's CEO says that AI will have more impact than electricity or fire. Another expert says that if your business doesn't use AI, you will go out of business. The National Academy Commission on Data Science Education recommended that data science be taught as a new paradigm at all levels of education in parallel with math and the scientific method. And we all know that the largest, most successful companies in history are also data science leaders. Gartner says that data science has unlimited potential in business, but it's very hard to think in data. We will come back to this challenge that I call data science acumen. The significance of data science can also be seen in intense international competition. The Economist newspaper used the 4 pillars of data science, the essential resources required for data science, to compare competing countries. The data advantage goes to China. The hardware advantage goes to the USA and the UK, but China has just produced a data science chip that beats others by a factor of 4. Advanced software goes to the US, but most is open source, and this may change. And the labor advantage goes to China, with 300,000 inexpensive labelers working in data factories. These resources, plus knowledge, experience, and investment, produce IP in winner-take-all markets. The significance, looking at what the economist calls the digital Cold War, measured in capitalization of data science leaders, data science competition looks like a 2-horse race, North America versus China. It's actually a 1-horse race based on the US's ability to invest, develop, and deploy data science. Clearly, business, analytics, and analysts and governments consider data science to be very significant. But as this isn't my area of expertise, let's look for metrics of data science significance based on technology. But first, an observation about metrics. The most visible indicators are often poor metrics. For example, 60% of Americans invest in the stock market, most using stock market indices like the Dow Jones as a metric to buy or sell. But as Nobel Prize winning economists have told us, stock market indices are very poor metrics. Let's take a look. The continuous jagged pattern of the 2019 Dow Jones is typical, and as is repeated here in 2018. But let's look closer at these little ups and downs. This is a V-shaped recovery, a dip followed by a recovery in minutes or hours or days. There's no fundamental change. These are usually caused by inexperienced investors, or it's a tactic by strategic investors. Let's look at another pattern. Similarly, a W-shaped recovery is economically meaningless. So the lesson here is that stock market indices are widely used, but they're poor metrics for investments. The best investment metrics are based on the fundamentals of the investment. Similarly, in data science, the best metrics of data science significance are based on the fundamentals of data science. So let's consider the typical metrics used to measure data science significance. Throughout my career, data has grown exponentially and will continue to grow exponentially for decades. Let's see why. New technologies continue to fuel massive data growth. 30 billion new Internet of Things devices will constantly stream more data, made more accessible by 5G, accelerating the growth of data and its use. Digital models used to design and develop products are now sold with the product to aid the management and maintenance, specifically of very large, complex products like jet engines, but now used for vehicles, and more recently for activities like architecture used here in the restoration of Notre Dame. These technologies contribute to, but they don't explain, decades of data growth. This chart does, since most developed countries are less than 20% digitized, with years of data growth to come. So in conclusion, data will grow exponentially for decades, but data is not a success metric, it's a challenge metric. These challenges preceded data science that now magnifies them with massive scale and new paradigms we don't understand. Man has created models for most important areas, like quantum mechanical models for the infinitely small and astrophysical models for the infinitely large. After centuries of dealing with data in critical areas like finance, we have no model for understanding data. We don't even know what its value is. So overcoming these challenges to master problem solving with data requires what I call data acumen, which is more than just the knowledge needed to reason about the data to overcome these pervasive technical challenges, the new paradigms, and data at scale beyond imagination. Data acumen is the wisdom to use that knowledge for data science-based discovery. Consider an analogy with cooking. Line cooks have knowledge to cook many dishes. It takes a master chef like Ferran Adria here with the wisdom to master the menu and gastronomy. But in data science, we don't even yet have the knowledge. Hence, the wisdom to use that knowledge, data acumen, is at least a decade away. Now consider analytics growth, a typical metric of data science significance. Early spectacular successes of data science analytics in business include UPS route optimization for 16 million shipments a day that saved them 100 million gallons of gas over 10 years. Another is Southwest Airlines that saved $100 million a year managing its fleet of 700 Boeing 737s, and the US Internal Revenue Service saving taxpayers $2 billion a year by improved detection of fraud and detection of improper payments with data science. These spectacular successes led to widespread data science adoption and massive analytics growth. Additionally, superhuman performance of data science in areas like natural language processing and image recognition have led to new businesses in fields like communications and medicine. Business analysts project exponential growth in market value to grow to $100 billion by 2027, and demand for data scientists and engineers exceeding supply by millions. These projections are made by analysts who are not experts in data science. For example, the demand for data scientists is about to disappear. Those are more marketing beliefs than projections. Rapid industry adoption does not mean rapid industry success. 90% of large firms claim that data science is their key to transformation. However, only 20% of those have successfully deployed it. In research, as chair of the scientific advisory board of a large data science research institute, I witnessed the growth of data science institutes internationally from 20 in 2013 to thousands in 2020, with one in every university and R&D lab. What's even more astonishing is the number of research papers published in data science. In 2018, 100 machine learning papers were published every day, producing 30,000 that year, doubling to 60,000 in 2019. Truly astonishing. Analytics growth comes with spectacular failures due to limitations in data science. Spectacular failures include data science applications that lead to racism, bias, and death. One limitation of data science is both amazing and incredibly obvious. If the answer to a problem is not in the data, then data science is not going to find it. This excludes critical cases called 1% cases, like the failure of a nuclear plant, the failure of electrical grid, earthquakes, and any problem that is highly dependent on human judgment. Another limitation of data science is that its models are not robust. They're fragile. Slight changes in the problem, the model, or the data may cause a failure that you may not even detect. Hence, it's not so safe for critical decision-making like medical treatments. In conclusion, the analytics is challenging due to data science's inherent complexity, such as models consisting of billions of variables and trying to select the best model from 10,000 choices, such a complex decision that it has now been automated in a technology called neural architecture search. These complexities, plus new paradigms in data science, make it extremely difficult to understand and deploy, explaining why most industrial applications of data science fail. As with data, we have yet to develop the knowledge to solve analytical challenges, let alone the wisdom required for safe, robust data science. So in summary, achieving data science acumen is an inherent challenge of data science. Data science acumen, the wisdom underlying the principled extraction of insights from models, requires data acumen, how to reason about data on its own, combined with analytics acumen, how to reason about analysis on its own. So to summarize data science significance metrics, data growth is a challenge metric. We don't want more data. We need to solve long-standing data challenges. Analytics growth is a true measure of real data science discovery, successes, and failures. Analytics belief, non-expert speculation in business versus data science, are typically poor metrics. And finally, the investment made in data science research is an excellent metric of the significance of data science. They say that if you are constantly amazed by something, that you don't understand it. So this is my declaration that I will not understand data science for quite a while. Data science will continue to be applied everywhere in many, many new domains with significant challenges, risks, and failures, and data science will continue to amaze all of us. Over the next decade, data science will emerge as a more mature, multidisciplinary field, but it will not be a hero's journey as legend has it. It will be much messier and will depend heavily on collaboration. Legend has it that medieval wars were won with swords wielded by master swordsmen like Sir Galahad. In reality, and more importantly, victory depended heavily on swords crafted by master swordsmen, usually anonymous. To be more precise and more messy, medieval wars were won by massive bands of swordsmiths, swordsmen, soldiers, cooks, horses, all collaborating intensely to win the war. Legend has it that data science problems are solved by data scientists. This too is a myth. In fact, data scientists may soon disappear. But like medieval wars, data science depends directly on collaboration across teams of data experts and analytics experts and across many disciplines, and most importantly, application domain experts. So over the next decade, data science challenges will be resolved in world-class industrial and academic labs that have the required resources, researchers, developers, practitioners across many disciplines, domain expertise, and data to build, design, and train models like GPT-3, one of the most successful language models that cost $12 million to train. In reality, only the largest industrial labs can afford to maintain world-class data science research and development teams. Universities simply do not have the resources. To see why universities can't compete, look at the prodigious output featured in the annual developer conferences of Apple, Amazon, Microsoft, and Google that you can readily find just by searching for them on the web. Industrial labs will produce data science platforms that will automate comprehensive data science workflows. As data analytics will be embedded in most applications, data science platform functionality must be embedded into enterprise architectures. Hence, they will disappear as standalone components, as is already occurring with AutoML. Hence, the data scientist role, described a decade ago as the sexiest job in the 21st century, will soon be obsolete. Responsibilities claimed to be those of the data scientists are being automated. First, end-to-end data science workflows, and second, selecting the best model from 10,000 candidates exceeds human comprehension, so it's already been automated with neural architecture research. In any case, data scientists needed to ensure collaboration across data science teams, something they seldom did. Now for a very cool idea, what I call the basis of the next generation of computing. Recall that data science is model-driven and that data science is the principled extraction of insights from models. In addition to data science's new paradigms for reasoning and computation, data science motivates a new computational architecture that I call model-driven computing. Unlike the other two paradigms, it's easy to understand. It'll be so obvious that you may wonder, what's so great? Problem solving in scientific and math-based fields are model-driven. Once we understand a discipline, we build a model with which to solve problems. For example, climate change, genomics, and supply chain management. Models are typically built into automated systems to drive solutions. This may not be so evident as models are typically hard-coded into the system, making the model indistinguishable from the system. For example, in 2000, SAP's supply chain model was hard-coded into their supply chain solution. A far better solution is to extract the supply chain model from the system and have the system support any supply chain model that is in a library of acceptable models. This makes the computing architecture model-driven. Elsevier's client path system is a model-driven data science solution that is driven by an endocrinology model from medicine and uses data science to analyze patient conditions to recommend treatment plans. Most data science platforms take advantage of data science's model-driven nature. For example, TensorFlow can run any of hundreds of models in its model library. Model-driven architectures are extremely flexible, capable of supporting a wide range of models, and they apply far beyond data science to all model-centric domains. Hence, like data science platforms, I suspect that the next generation of computing will be model-driven. So models are the basis for data science reasoning and computation paradigms. They are the basis of the next generation of computing for both data science and conventional computing. Hence, models will be developed and sold in model markets that will be dominated by the vast number of conventional versus data science models. I claim that model-centric problem solving is far more realistic than conventional problem solving and programming. However, it can also be more complex, and it critically requires collaboration, as is the case in data science. And let me show you why. Medicine consists of 120 specialties, each based on one or more models. To deal with multiple highly interrelated medical conditions of a patient, specialists collaborate. For example, an endocrinologist would not pursue an endocrinology recommendation without consulting other relevant specialists. Like medicine, most real-world problem solving involves multiple models, making collaboration critical to most realistic problem solving. Multimodal problem solving is already well underway in data science. BERT, a single model and the most successful language model in 2018, was surpassed in 2019 by GPT-3, a multi-model language model. On further analysis, BERT was found to be composed of multiple models as well. Multiple models are often far better than a single model. After all, most models can't capture all features of interest. Ensemble modeling uses many models. For example, in forecasting a hurricane, you want to know if you're going to be under threat from any potential path. Veridical data science is a new, innovative method of ensuring more robust data science using many models. Transfer learning is a leading methodology of developing a model based on an already proven model. And with data science embedded everywhere, models will be everywhere. Since everyone is familiar with how medical specialists collaborate, I'll use medical collaboration as an analogy for collaboration in data science. There are at least 4 types of collaboration. Cross-disciplinary collaboration considers information in one discipline from the perspective of another. A brain surgeon considers advice from neurologists. In data science, data experts consider advice from statisticians. Multidisciplinary collaboration uses multiple disciplines, possibly combining them, but not integrating them. Multiple medical specialists confer about a single patient. In data science, experts in multiple disciplines develop a single data science workflow. Interdisciplinary collaboration creates a synthesis across disciplines. In brain surgery, synthesizes a plan from guidance from multiple specialists. In data science, we saw that data and analytics experts synthesized a unified solution that was 2,000 times better than each solution on its own. Transdisciplinary creates a unified view from multiple disciplines. Over 2000, we all saw multiple medical specialists develop an understanding and treatment of coronavirus. My research in data science it attempts to be transdisciplinary, which I will now present. To summarize our discussion so far, data science is one of the most significant innovations of the 21st century, with superhuman successes, risks, and failures. It introduces new paradigms of discovery, computation, and next generation computing that may surpass the scientific method in significance, but certainly in applicability. Data science is in its infancy with untapped potential for success and failure. It's extremely complex, it's not fully understood, and possesses many challenges. So how do we address these challenges to achieve safe, robust data science? Michael Jordan, the UC Berkeley statistician and data scientist, and many others have observed that data science lacks both an underlying theory and an engineering practice. He illustrated the need for these using physics. For most of human history, buildings, bridges, and roads were built based on our knowledge of physics and building experience. Some of them fell to the ground. As structures became more complex and larger, our knowledge of physics and experience was inadequate. We were missing an engineering discipline with its principles of analysis and design. This led to the development of civil engineering based on concepts from physics and underlying principles for applying them in practice at scale. By analogy, safe, robust data science requires both the data science theory, consisting of concepts with underlying principles, and data science engineering, principles for applying those concepts in practice. However, data science engineering poses fundamentally new and much harder challenges than we have ever seen before. Data science is widely used in medical systems, so you can imagine a nationwide inference and decision-making medical system that makes life-critical decisions using data science at massive scale. Of course, life-critical decisions will be made by data science applications at all scale, including the app that drives your autonomous vehicle. Conventional engineering must ensure only that complex systems operate safely and robustly, already a decades-long challenge. Data science engineering must go much further to ensure that applications are safe and robust. In medical systems, this means they have to follow the Hippocratic Oath. First, do no harm. Where do we even start with such a challenge? So my research addresses these challenges based on this hypothesis: to establish, over a decade, the foundations of data science, including data science theory, that I call the science of data science, and data science engineering practices. In the data science reference framework, I will develop a definition of data science that is principled, for example, safe and robust; comprehensive, bringing together results from all data science subareas; multidisciplinary, because data science concepts are derived from many disciplines; and will evolve over at least a decade as a multidisciplinary activity of the worldwide data science community in an online open access journal. And this is not as easy as it may seem. For example, we can easily get a statistician to define a statistical concept, but how do we get them to collaborate across disciplines? So let me show you my plan. Data science is the principled extraction of valuable insights from models. Principles are the basis for the science of data science and data science engineering. So we need to identify and define the concepts and the principles. How do we find them? Happily, most already exist in disciplines from which data science has been derived. A theory consists of a number of concepts formally defined by foundational principles, that is the theory, and engineering principles that define the engineering practice. Collectively, the data science concepts constitute data science. Data science concepts plus the foundational principles constitute the science of data science. And the data science concepts plus the engineering principles constitute data science engineering. Having defined over 300 such concepts, I have found identifying and defining concepts are pretty easy. Identifying the principles are a little harder, and defining the principles formally is really challenging. So the data science reference framework will consist of data science concepts, the data science foundations, the engineering principles, and these are all brought together by the data science workflow that is key to the development of the framework and to its use through multidisciplinary collaboration. Let me show you the trick. Data science concepts are derived from many disciplines. A concept from a source discipline like AI or data science or mathematical foundations are mapped to the corresponding derived data science concept as it is used in a data science workflow operation. A simple example is the AI concept of machine learning maps to the data science concept of machine learning. This simple map is obvious, but it occurs frequently as most data science concepts are derived from other disciplines. And here is the trick. The bidirectional maps map derived concepts back to the source discipline concept. So this is how the framework will be developed and used by researchers, developers, practitioners, and educators. So let's say you are a researcher and you want to understand the training data set operation used to extract a training data set from an input data set. You use the maps from the training data set operator to find relevant concepts in other disciplines. In this example, we found 7. This is where the multidisciplinary collaboration comes in. You can study the concepts on your own, or you can reach out to other experts in those disciplines. Either way, you achieve collaboration. Let's say the disciplines were let's say that 3 disciplines were useful. Data systems provides the concept of data set partitioning. Statistics provides three relevant concepts: that the set size must be statistically significant, yet minimally impact the source data set. It must be random sample, and it must be representative of the complete set. Finally, computational foundations provide concepts for optimizing the computation. With each concept, we found the principles required for safe, robust solutions. In conclusion, I have attempted to convince you that data science is one of the most significant innovations of the 21st century. It introduces new paradigms of discovery, of computation, of next generation computing that may surpass the scientific method in significance, but certainly in applicability, applying to all problems for which there's adequate data. It currently exhibits amazing superhuman successes, risks, and failures, and it is in its infancy and will take at least a decade to mature. Due to its complexity, challenges, and new paradigms, we are just beginning to understand it, let alone achieving data science acumen, which is a prerequisite for safe, robust data science that I am pursuing in the Data Science Reference Framework, a collaborative, multidisciplinary online journal. Returning to our initial hypothesis, it's obviously far too early to predict, but I hope I've convinced you of the significance of data science and of its potential to address existential challenges like saving the planet and saving humanity. On that note, let me offer an epilogue. Technology has driven two revolutions that have transformed our world. The printing press led to the Renaissance. Steam engine led to the Industrial Revolution. At the beginning of this talk, we saw that technology is currently driving change globally and exponentially, more extensively and rapidly than ever before in human history. Data science is only one of many new technology-driven paradigms at play. Technology is being used to capture everything we do and say, drive our cars, influence our politics, communications, even truth, edit our genes to change human life, provide personalized medicine to cure previously incurable diseases, and connect our brains to technology, redefining the human-machine boundary. So perhaps the 21st century Renaissance is already underway. So thank you for your time and attention. I hope you found some things of interest and of value. The video and these slides will be posted on the conference website. I am happy to take questions in the remaining time. Please email me with questions, observations, disagreements, and especially if you are interested in participating in the Data Science Reference Framework. Thank you very much.